Hey everyone, how's it going? It is Josh, and today I will be talking about 4 types of reactions that you do or you will do in chemistry. And those reactions are going to be the synthesis reactions, decomposition reactions, single displacement reactions, and double displacement reactions. And if we have time, I might do some other types of reactions. So I'll be providing examples of each type of reaction. So let's get started. So a synthesis reaction. So a synthesis reaction, it's 2 or more reactants combine to form a new product. So this is the algebraic way of doing it. I'm not going to do that. I'm just going to get straight into the chemistry, all right? So it's a synthesis reaction, to repeat one more time. It's 2 or more reactants combining to form a new product, all right? So let's get rid of this, and let's just use this periodic table, all right? So let's use sodium right here and chlorine, okay? Chlorine over here, right? So how am I going to write this? So this is a synthesis reaction, all right? So let's say we have sodium and chlorine, all right? So you add chlorine. And don't forget, there's a diatomic for chlorine because it's just one of those diatomic elements. If you don't know what diatomics are, then you can find out what it is on YouTube. Plenty of videos for those. But as you can see here, you know what? Let me write it a little lower. Actually, let me just... actually, I can't angle the thing. Let me see if I can... Maybe... There we go, and I can write it here. Okay. So sodium plus chlorine, okay, in the diatomic. And what does that go to, or what does it react to? Well, sodium has a +1 and chlorine has a minus, right? And we know that when you combine chlorine with another element, you don't need the diatomic anymore, right? So a plus and a minus cancel each other out. So therefore, it's sodium chloride, all right? And that is an example of a synthesis reaction, all right? Very simple. You're just combining 2 or more reactants to form a new product, all right? So before, this was sodium plus chlorine. Now it became sodium chloride, all right? Simple. So the next type of reaction we have is a decomposition reaction, all right? And this is when a reactant breaks down into 2 or more let me read that again. This is when a reactant breaks down into 2 or more simpler particles, okay? So we'll use the same example here. So we have sodium chloride, all right? And it has to break down, right? A decomposition reaction, okay? So what does it break down into? Well, it's pretty simple. It's just the reverse of what we did up here. Sodium plus chlorine. And now that chlorine's alone again, you have to add that diatomic, all right? So that is an example of a decomposition reaction, okay? Let's move on. So 2 more reactions, might do more if we have time. So sorry, you can't really read the writing here, it's very dark, but I will read it to you. So hopefully you can get the gist of it. You can't read that, I know. So single displacement reaction. So it's when one particle appears to move out of one compound and into the other, all right? So I'll show you what I mean by that, or what it means by that. So, oh wait, no, maybe I should read the full thing first. Okay, I'll start over. So this is a single displacement reaction is when one particle appears to move out of one compound and into the other, all right? Single displacement reactions occur when A is more reactive than B. That's referring to this algebraic example. Don't worry about that. So the 2 types of synthesis reactions are when you have 2 cations competing for 1 anion, or 2 anions competing for 1 cation, all right? And it's important to note that when you have 2 cations competing for 1 anion, use the metal activity series to determine whether there's going to be a reaction or not. I'll show how you use it in a couple seconds. And if you have 2 anions fighting for 1 cation, always assume the reaction will occur. And I'll show you what that means in just a sec. Let me just get a sip of water. Sorry, not gonna edit this out because I don't want to. All right, so we'll start off with the single displacement reaction where you have two cations competing for one anion, all right? So I love using sodium. I feel like it's very simple and easy to use, and it's good not to change things up too much. So now we don't need this, okay? Just forget about this. That this was synthesis and decomposition. We're on to single displacement now, okay? So let's say we have potassium bromide plus lithium, okay? So this is going to be a single displacement reaction, all right? You have two cations. It's potassium and lithium competing for one anion, and that's bromine, okay? So basically, bromine is going to end up with either potassium or lithium, okay? But which one does it end up with? Well, this is when you use the metal activity series, because you have two cations fighting for one anion. You only use the metal activity series when you're in this situation. So basically, metal activity series is MAS, so it stands for metal activity series. So as you can see, elements that are higher up are more reactive. So lithium's the most reactive, and gold, I believe, is the least reactive, okay? So basically, the anion will always go to the element that's more reactive. The element that's more reactive will always take the anion, okay? So in this case, you have potassium. I'll circle it. The ones in the square are cations, right? Lithium, as you can see, is more reactive than potassium because it's higher on the metal activity series. So that means lithium's going to win bromine over, okay? So the equation is going to change to potassium plus lithium bromide, okay? And as you can see, it appears that one particle moved out of one compound and into the other, right? Bromine moved out of this compound into this compound, okay? But we know why, because lithium is more reactive than potassium, okay? So that's when you have two cations fighting for one anion. Now, what happens when you have two anions competing for one cation, okay? Well, as I said earlier, if you have two cations fighting for one anion, okay, you have to assume the reaction will always occur, okay? So let's say we have, what am I going to do here? Let's say it is carbon, nitrogen, I don't know what we use here. This is a tough one, actually. Let's just say we use, okay. Let's say we use sodium oxide. So sodium oxide and fluorine. Okay, so you have two anions, oxygen and fluorine, and one cation, sodium, okay? So sodium has a +1 charge, oxygen has a 2-, so that's why you need two of the sodiums, as I put right here, to make it equal with oxygen. And fluorine is one of those elements that needs the diatomic when it's by itself, okay? So I said, always assume the reaction will take place, okay? So that just basically means the cation will just go to the other anion, okay? So it's going to do this. It'll become sodium fluoride, okay? Fluorine has a minus charge, sodium has a plus charge, so you don't need any extra of each. It's just 1 and 1- cancel each other out. Plus oxygen, you need the diatomic because oxygen is one of those elements that has a diatomic, okay? So hopefully that's pretty straightforward. The reaction will always occur when you have two anions competing for one cation, okay? And I did forget to address this earlier. Let's say this is for when you have two cations competing for one anion, all right? Let's say you have lithium and oxygen, okay? and you have potassium. Okay? So here you have two cations, lithium and potassium, competing for one anion, which is oxygen. Okay? You need two of the lithiums because lithium has a plus charge and oxygen has a 2 minus. That's why you need two of them. Okay? Well, if you go back to use this metal activity series, which is reasonable because when you have two cations competing for one anion, you have to use the metal activity series. You can see that lithium is more reactive than potassium, but it's already with the anion. So what do you do now? Well, when you have a situation like this, there's no reaction. So you can write no reaction, or NR for no reaction, okay? Because lithium, which is more reactive, already is with the anion. So there's no reaction. It's not going to happen. Okay? So basically, to summarize that, if you have two cations fighting for one anion, okay, use your metal activity series to see if there's going to be a reaction or not. Okay? And if you have two anions fighting for one cation, always assume the reaction will take place. That is single displacement reactions, okay? And now, I think we won't have time to do any extra, but the last one, which is double displacement reactions. So double displacement reactions are when anions and cations of two molecules switch places, and I'll show you what I mean by that. So, I'll use the example, silver and nitrates, okay? And you can add that to hydrochloric acid. Okay? So, first of all, it's important to note that in order for a double displacement reaction to occur, you need to have two cations and two anions, okay? If you don't, it's not going to be a double displacement reaction, okay? So, silver is a cation. It can either be, let's resort back to this metal activity series. It can either be periodic table. My bad. It can either be 2 plus or a plus. And nitrate, diatomic, nitrate. NO3, it's a minus. So we know that the silver has to be a plus. Okay? And hydrochloric acid, well, hydrogen's a plus and chlorine's a minus. So even already, okay? So as you can see, I'll circle the cations and underline the anions. You have two cations and two anions, okay? So, in double displacement reactions, the anions and cations will switch places, okay? So basically, silver is going to combine with chlorine and hydrogen is going to combine with nitrates, okay? So, here, the charge of silver is 1, so keep that in mind. It's 1 and not 2 plus. So, chlorine's a minus, so it's going to become silver chloride, right? Plus, hydrogen's a plus, nitrate's a minus, so nitric acid, okay? Now, let's just say, nitrate had a 2, so it was in the brackets. Let's just put it up down here. It's in the brackets. Let's just say it at a 2, okay? That would mean the charge of silver would have to be 2 plus to keep it balanced, right? And if it were a 2 plus, you'd keep that in mind when you switched it, like when you would combine it with chlorine, okay? So it would be AgCl2 because in this case, it was a 2 plus and chlorine's a minus, so you need 2 minuses for it to be 2 minus. 2 plus and 2 minus cancel each other out, okay? But for this example, the one I was doing, it's not a 2 plus, so that's why it's AgCl, okay? So hopefully that didn't confuse you too much. But basically, this goes to this, AgCl plus nitric acid, all right? So that's about it. I don't think I'm going to do another example, but that's what a double displacement reaction is, okay? So some final notes, basically a summary. How do I get this into frame? Okay, here it is. All double displacement reactions will occur. I forgot to mention that. They will occur, okay? All single displacement reactions involving two anions fighting for one cation will occur. Yes, they'll always occur. You switch them. And if you don't know what I mean by switching them, just go back in the video and I explain what I meant by that. Okay? When two cations compete for one anion, consult the metal activity series to see if their reaction will occur. And as you can see, with the examples I provided back then, it is possible for it to occur, for a single displacement reaction to occur with two cations and one anion, and it's also not possible. Depends. So that's it for today's video. So we did synthesis, decomposition, single displacement, and double displacement reactions. So I hope you enjoyed that video. This is still one of my first videos, so sorry if it was pretty garbage. If it was confusing and you didn't understand it at all, please let me know in the comments. If it did help you, then feel free to, just give it a like, maybe subscribe if you're feeling generous. But I'll see you guys in the next video. So peace out, guys.